So we were working all the time on this project, and I really enjoyed it. And I would like to share this feeling that I have about this paper with you all. So so I divided my talk in 5 topics. I will start with some historical background, and then I will move to some concepts. So I will define two different types of norm attainment. So first of all, I will define norm attainment on the tensor product, and then I will move to the nuclear operator settings. So I will give you the first examples in both definitions, and then I will present an example where this doesn't hold. So it makes sense to talk about density then. Okay, so that's the thing that I will be talking next. This is the approximation that I put here, and then I will give you a context sample which shows that this doesn't work always, and then I will present some open problems on this topic. Okay, but also I'm presenting some further research that we can discuss at the end of the talk. Okay, so let's talk about some historical background on this topic. So I mean, first of all, I'm really sorry because I think Martin already gave a lot of background in his talk some months ago. So I will be kind of repeating some of the stuff that he already talked about, but it's necessary. Okay, we will be talking about functions which attains the norm. So we start with functionals, which is the starting point of this theory, and we say that the functional attains norm when the supremum of its norm is actually a maximum. Okay, and it's very natural to ask what is how many functionals on the set X have this behavior. Okay, and for me the step 1 in this theory, it's not the Bishop-Phelps, but the James theorem, which characterizes reflexivity of Banach spaces. So the James theorem says that when Banach space is reflexive, everybody has this behavior that I was talking about before. Okay, but on the other hand, if you are in C0, for example, it's very simple to construct functional which never attains the norm. For example, by taking a sequence which converges to 0. So you take from certain point is strictly smaller than 1. So it's very easy to construct a functional which never attains the norm. So it makes sense to talk about density of these guys in the dual operator. So the question here is, if you give me a functional in the dual space, is it possible to approximate it by functional which attains the norm? So Bishop and Phelps asked this question in a positive, saying that for every Banach space you have this kind of density. Okay, so at the end of this article they ask if this is true also for the most natural step, which is for operators. Okay, and of course, but at the same way that you define norm-attaining functionals, you can define norm-attaining operators by the same definition. And the Bishop-Phelps question was that if you give me an operator, is it possible to approximate by operators which attain the norm? So this is the Bishop-Phelps question, and Lindenstrauss came up with the first context sample when this density doesn't hold in general. Of course, after this context sample, Lindenstrauss opened the gate for a lot of research on this topic. And just to mention some, I hope that I didn't forget, for sure I forgot a lot of people here because the literature on this topic is quite huge in that sense. But just to mention some names of people who've been working in this topic for a while, for example, in norm-attaining operators. So they just continue the Lindenstrauss work. And then many people moved to the bilinear mappings. And then more recently, people were working with homogeneous polynomials and also holomorphic function and etc. Okay, so also nowadays people are working in Lipschitz functions, Lipschitz free spaces, and all this kind of stuff. So I just wanted to mention some people just to show you how important this theory became after Lindenstrauss, and people were working on this topic all over the world. Okay, so let's move a little bit to the main questions that I would like to consider here. So the first question, it was an old question posed by many authors during this the time, like around the 70s, for example. If every compact operator can be approximated by Norm-Attaining ones, and it turns out that the answer for this question is negative, and Miguel Martin was the one who solved this question in the negative by presenting a compact operator which cannot be approximated by Norm-Attaining operators. So Miguel used the counterexample on approximation properties, and he was succeeded by in 2014 by presenting this counterexample. Okay, so the main question, actually Miguel gave a talk some months ago, and he himself said that this is the main question, and I agree with him that this is the main question, the main open question right now in the theory of Norm-Attaining. Either finite rank operators can be approximated by Norm-Attaining operators. So in that sense, I consider our paper one step further in the theory of Norm-Attaining, because I would say that our job is something like in the middle of these two guys here. Because as you will see, I will explain this after, that every nuclear operator is compact. So every nuclear operator can be approximated in Norm by finite rank operators. So I would say that our work is something in the middle here. And in this sense, I would say that, and I hope that this can happen, that our paper is one step further in the theory of Norm-Attaining functions. Okay, so let's start with the talk itself. So I will be talking now about nuclear operators and tensor products. So for this, I will need to steal some of the things that Abraham already explained to you last time that he was talking about tensor products. So I will just steal from him the definition of projective tensor product. So you take two Banach spaces and then you construct the projective tensor product by completing the norm space x times y endoided with the projective of the projective norm. Okay, I don't know if you remember that, but in his talk he was explaining to us what is the difficulty here of calculating distances in this space. Of course, he was dealing with the geometric characterization of the Daugavit property, but here we are interested also of calculating distances. So, for example, to take an optimal representation here, such that you can calculate norm, is a pretty difficult job, as he was explained in his talk. Okay, but here we are doing the same kind of a strategy that he was using for the Daugavit property by kind of trying to get rid of the projective tensor product languages and move on to something that we know. For example, the dual of the tensor product, the projective tensor product, is nothing more than the operators from X into Y star, given by this action here. Okay, so we will be doing this all the time. We are trying, as I said before, get rid of the projective tensor product language in the sense that we are always trying to identify the dual of this space with the operators from X into Y star. Okay, but also we can connect this with the bilinear forms on X times Y. So this is one of the things that we'll be doing as well here. Okay. So let's move on now with the definition of nuclear operator. So you have a canonical operator J here from X times Y into L of X, Y with norm 1. Okay, how you define this canonical operator here? So you take a representation here, U of like this, and you associate this U as into an operator. And this operator is has an action on at X like this. Okay, so this is an operator from X into Y, and every operator which arrives like this, it will be called nuclei operator. Okay, so we have the whole set of this kind of operators, and we have also a norm here, and this norm is nothing more than the projective, somehow the projective norm on this space, which is the infimum of all these guys when you take over all the representations here of T. Okay, so the first thing that I would like to mention here is the thing that I already told you before. If you take a look at the expression of T here, you see immediately that every T is nothing more than the limit in the norm of finite rank operators. So this implies that every nuclei operator is compact. Okay. So second thing that I would like to mention here is that when you take a look at this expression here, you might think that this is nothing more than the projective tensor product of X star with Y, which turns out to be false because the J that I was talking about before is not always injective. And this means that the nuclei operators from X into Y can be identified with X star, projective norm with Y, quotient, the kernel of J. Okay, so this will make a big difference between the projective tensor product and the nuclei operator when we're talking about Norm-Attaining, because we will have two different concepts. Pay attention that every time that we are working with a nuclei operator, you have to deal with classes and you have to deal with quotient in general. Although you know by some results on approximation properties that when one of the factors here has the approximation property, the kernel actually is 0, and then you have the equality here. And then our concept will coincide at the end. But in general, that's the best thing that you can say about the nuclei operators. Okay, so yes, so that's the thing that I would like to mention about the definitions, and I would like now to move to the norm attainment concept. So let's start with what we mean by a tensor attaining the projective norm. So this is nothing more than we say that the Z here in the projective tensor product of X and Y attains its projective norm when the projective norm actually is attained. I know that sounds very obvious, but this is the most natural way that we found to define this concept. And of course, we say that T attains nuclear norm when the nuclear norm is attained. Okay, so this is exactly the concept that we are working here. As I said before, in general, when you are working with T in here, you have to deal with the quotient space, and although that the proofs are quite similar to each other, you have to deal with the quotient space. So in some sense, the proofs for the tensor product is much cleaner in this sense, because in this case you don't have to deal with the quotient space. But even though every result that we have for one of them, we have the counterpart for the other one. So that's the thing that I will be doing here. Every result that I have here for the tensor product we will have the counterpart for the nuclei operators. Okay. So just to make sure that we are speaking the same language here, let's put some names, some notation that it's necessary. So NA of XY will be for the whole operators, for all operators from X into Y, which attains the norm in the classical way, the first definition that I gave to you before. Okay. The NA of X times Y will be the classical definition of a bilinear form attaining the norm. NA pi of X and Y will be for the projective, for the projective tensor product. So Z attains projective norm, and NA of N will be for the nuclear operators which attain the nuclear norms. Okay, so I think the notation is pretty similar to each other, but I think it's quite understandable in this sense because you have pi here, you have N here, and these are the classical ones that everybody knows. Okay, so now we can move to our results on nuclear operators and tensors which do attain the norm. Okay, so like I said before, the good thing that we have here is that we can indeed get rid of the tensor language by doing the following. So we have this theorem here. So we take Z in this space here in the projective tensor product of X and Y like this. So it has a representation. So the following are equivalent. You have that Z attains projective norm if and only if exists G, okay, in the sphere of L of X and Y star such that you have this. So pay attention here that this is much stronger than just saying that G attains the norm. It says that G attains norm in a lot of points. Okay, it's not just attain the norm as an operator in X on X. It's attained the norm has a bilinear form actually. Okay, because it's attains in both points here at both points. And also this is equivalent to the fact that for every G here which norms the Z satisfy the same condition as before. So to prove this, you use merely convex arguments. Okay, it's not difficult to prove this theorem, but this will be very useful because, like I said before, we are stopping working directly with projective tensor products, and we are moving here to operators which satisfies this condition here. So like I said before, pay attention in this because we will use this in later. Okay, that the fact that this G here attains the norm has a bilinear form, and it attains norm at a lot of points. Okay, so like I said before, you have the projective tensor product version of this theorem. So you have a nuclear operator version of the same theorem. So you have the representation for T here. So the following are equivalent. You have that T attains nuclear norm if and only if exists this G here in an annihilator of the kernel of G with norm 1 satisfying the same condition as before. And then you have that this is equivalent to the fact that this is for every G with the same condition, norming the T here. Okay. Again, the proof is done by convex argument, and now by using the kernel of G and all the story about the quotient that I was talking to you before. Okay. So before moving, I would like to share another screen here. I don't know if I can do it. So I will try to I don't know if you can see that. Can you see this?
Yes.
Okay, good. So I will just show you one way to how to use this characterization that we just proved. Okay. So I will show you here that there are nuclear operators which attain their norms. They are nuclear norms, but they don't attain the norm in the classical sense. Okay, by using the characterization that I was talking about before. So for this I would take let Y be an infinite dimensional strictly convex Banach space. Okay, so you take here L Yn in the sphere linearly independent. And by using the Harmonic Theorem, for each n, you can take Yn star of Yn equals to 1. Okay, so these guys here are in the sphere of the dual of Y star. So I'm constructing now the operator which will give us the things that the one of the properties that I was talking to you before. So define phi from y into L infinite, such that for every y you associate this sequence here. Okay. So of course, this is linear, this is continuous, this is everything that you want. This is well-defined because of the yj are in the sphere. The norm is smaller than 1, phi is continuous. But the most important part here that I would like to emphasize is the following one, that phi of yn of En is equals to 1 for every n, where En is the canonical basis of L1. Okay, so now we can define T from C0 to Y by T. T will be the sum of 1 over n, En times En. And this is in C0. No, this will be in L infinite. I'm sorry. Tensor product with Y. Okay. So because of this property here, and because of our characterization, T is a nuclear. It's a nuclear operator which attains its nuclear norm. But on the other hand, pay attention here that this guy, it's not finite rank. And then we have this result here by Miguel Martin, that Miguel says that when X is a closed subspace of C0 and Y is a strictly convex, the set of all Norm-Attaining is inside the finite rank operators. And here we are dealing now with C0. So this means that if T is not finite rank, this means that T does not belong to the set of Norm-Attaining. Okay. So I'll come back to the slides now. Can you see this?
Yes.
Okay, good. So so that's the thing. I use this characterization here to prove that there are operators that attains nuclear norm, but not the norm in the classical way. Okay. But actually, I told you, I just defined one operator from C0 into Y, which attains its nuclear norm, but actually this happens for every operator on C0. So every nuclear operator on C0 attains nuclear norm for every Y that you take. And since I told you before, C0 has the approximation property, so you have the same result for L1 times Y. Okay. So for me, personally, this result is important because if you have a phenomenon like this in a classical theory, I mean by say T, if it's Norm-Attaining in the classical way for every Y here, X must be reflexive by the James theorem, which doesn't happen here anymore. So for me, it's important this proposition here because of this fact. Okay. So this happens also if we are dealing with complex Hilbert spaces. I'm not presenting the proof here, but this you should use the theory of Eiger-Weyler and stuff to prove this. So when T is a nuclear operator from a Hilbert space into a Hilbert space, you have that every nuclear operator attains norm, and since Hilbert spaces have the approximation property, you have the same thing for the projective norm. Okay. Okay, so since we have these two results here, so it's very natural to ask ourselves if this kind of equality holds for every Banach space. So is it true that for every pair of Banach spaces X and Y, every nuclear operator attains nuclear norm? or for every pair of Banach spaces X and Y, every tensor attains its projective tensor product and its projective norm? So the answer will be no, and will be given by this proposition here. Okay, you take these two Banach spaces. So, and suppose that every element in the tensor product attains projective norm. What will happen? It will happen by using the Bishop-Feld theorem, the classical one that I told you before, that the set of all bilinear forms on X times Y which attain their norm will be dense in the whole space. In other words, you have this here. If you have this equality, you have denseness for bilinear forms. And as a corollary, you have that if you have this equality here, you have this equality here. And for all of you who understands better than me the classical theory of Norm-Attaining operators, you know that there are pairs of Banach spaces X and Y star which this doesn't hold or this doesn't hold. So for this, by knowing that, you get the first examples of tensors which does not attain the projective norm. In the following cases, for example, you have a counterexample by Hull, which says that if X is L1 of 0, 1 and Y star is strictly convex without the Randall-Nikodym property, we have that this set is not dense here. So in this case here, there exists some Z in the tensor product of these two guys here, which doesn't attain the norm. The same thing happens for the Gowers counterexample on bilinear forms. Gowers proved that the pair X times LP, it's not dense in general here for bilinear forms, and consequently, because of our proposition before, here you have the same phenomenon. B, for me, again, personally, it's important because here one of the factors are reflexive. So this should be compared to the fact that with Lindenstrauss, right? That Lindenstrauss and the reflexivity. This means here that one of the factors is not enough. One reflexive space in one of the spaces is not enough to guarantee that every tensor attains norm. Okay. And finally, another example is on L1 of 0, 1. So Yun-Sang Che proved that this is not the case for bilinear forms. And again, in this case, you have this phenomenon here. Okay. So by presenting tensors which does not attain the norm, the projective norm in general, now it makes sense to deal with density. And that's the thing that we'll be doing in the next slides. Okay. Now the question, of course, now the natural question is to know if we can approximate every tensor by tensors which attain the norm, and also the same question, the analogous question for nuclear operators. Okay. So surprisingly, I will be using here a property that Martin was talking about the other day. The LOO. So just please don't pay attention in the name because I know it sounds horrible, but we had a reason at that time to call this property LOO. But just take into account that this property we will use this property as a tool to deal with the density in our case now in the following way. So let's just remember what is this about. So you have that the pair X times Y Z satisfies this LOO for bilinear mappings. If you give me epsilon and the bilinear mapping with norm 1, such that every time that X satisfies this, there exists this guy here, depending on both of them, such that every time that X and Z almost attains norm with this eta here, there exists another pair X0, Y0, such that the same bilinear form attains the norm and the points are close to each other. Okay. So remember, so coming back to the characterization that I was talking to you in the first slide, remember the thing that I told you before? I told you that it's not just the fact that the bilinear form attains the norm just one point. Is that it attains the norm at several points, and that's the thing that this kind of property gives to you. So that's the idea behind it, and that's the idea why we use this property as a tool, because here we do have positive examples of Banach spaces X and Y and Z, which have this property here. For example, for finite, by using compactness, you always have this property. Actually, you have equivalence when the second space here is uniformly convex. So this kind of property here will help us a lot, because we are all the time dealing with bilinear forms on X times Y, and with operators from X into YX star. Okay, and we also has a characterization for LP and LQ spaces, and actually there are some reflexive spaces X and Y which fails this property. I know that this property sounds quite strict in this sense, that is quite strong, but at least we have some positive results, and we are putting some emphasis here in the case that both of them are finite dimensional, because of the things that I'm about to explain. Okay, so the theorem is the following one. So suppose that X star times YK has the LOO for bilinear forms. So you have this property that I was talking about before. So you have the denseness. So the denseness holds. Okay, and it has a corollary by using the results that I was talking to you before. If X is finite dimensional and Y is finite dimensional, you have denseness. And also, if the first space is finite dimensional, and the second one is uniformly convex, you also have the denseness. Okay, and analogously, you have the same result for tensors, for tensor products. Okay, like I told you before, we have the counterpart of for one to the other. Okay, so what is the strategy now? Okay, I understand you are thinking now that okay, Sheldon, you have a positive result, but I mean, how many Banach spaces do you have which satisfies this property? That's not that much. I know that, and that's the thing that we are dealing with this first part here. So we are trying to use the finite dimensional case in order to get more examples by using a property that I will explain to you in the next slide. So what is the idea? The idea is that you know that in the projective tensor product in general, it doesn't respect subspaces, but it does respect one complemented subspaces. So this is one thing. We have the result, the positive result, the denseness for finite dimensional spaces in both factors. If both is finite, you have denseness. So what do we need to get more counterexample to get more examples, positive examples, by using these two facts? Well, we need a property which guarantees you a lot of finite one complement subspaces, and that's the thing that we are dealing here. So we say that the Banach space X has the property P if you give me epsilon and a finite collection in the sphere of this space. We can find a finite dimensional subspace M, which is one complemented, and besides that, there are X1, Xn, which are close to the original points that you gave me before. Okay, so this turns out to be a very known property. If you study the book by Casazas on approximation properties, you will see that this is equivalent to the metric pi property. Okay. Well, we the authors thank Gilles Godefroy, Tommaso Russo, and Petr Hayek to point it out this, because we were using this. We were struggling to get a lot of examples of Banach spaces which satisfy this property, and they told us that this is very known concept, and it was in Casas's book, and it was called metric pi property. And it turns out that this book helped us a lot to get more examples of Banach spaces satisfying this property P. Well, I will be calling property P because Casas has had a reason to call it metric pi property, but in this case we are not entering in details about this, so I will be calling property just property P. Okay. The good thing about property P is that it's a lot of Banach spaces satisfies it. So, for example, Banach spaces with monotone Sheldon bases, all of the LP spaces, isometric produals of L1. If both of them has the property P, you can extend the property for the absolute sums. You can extend for every C0 and LP sum. You can extend for projective tensor product. You can extend for injective tensor product. Actually, you can extend for cross norms in general. So it's a very nice property in this sense that almost all the classical, what we consider as a classical Banach spaces satisfies it. Okay. And what was the result that we got? So the result that we got by using this idea that I was explaining to you before is the following one. If both of them have property P, you have the denseness. And how you prove that? So you take Z in the projective tensor product. Okay, so it has a representation, an infinite representation. Since we can just assume that this summation is just finite because we are dealing with density here. You can use our finite dimensional result and our property P. So you approximate every point by using the property P, and using that in each point in each Banach space you have this finite one complemented subspace, and then you apply the results for finite case in this sense, and you construct a new one which is close to the second one, which attains the norm. So that's the idea. You use in both factors and on X and Y this property P. You go down for the finite dimensional case. You apply the result here because you already know that in finite dimensional work, and then you go up again by constructing a new tensor which does attain the norm. So that's the idea behind it. Okay. And also one thing that I forgot to mention you is that when a Banach space Z has the property P, it turns out that it actually has the metric approximation property. So the nuclear version of this is just a consequence of the other result. Okay. So of course, like I said before, now you have thousands of examples of Banach spaces which satisfy this density here. In both cases, in the projective tensor product case and in the nuclear. So it is natural to ask if this happens always. You always can have denseness, and at least for the tensors, it's not the case for the tensor product. Well, I will explain to you after, but at least for the tensor case, this is not the case. Okay, so I'm not giving you the whole proof behind it because I would take 15 minutes just to reply how this counterexample works. But at least I will give you some of the steps that it's necessary to think, at least the idea behind of the counterexample. So we were able to present two Banach spaces, X and Y, such that the set of every norm-attaining tensor, it's not dense in the whole projective tensor product from of X and Y star. Okay, so what is the idea? First of all, the idea is, remember the characterization that I was talking about when it does attain the norm. So this set here is kind of norming for the projective tensor product. So you have to show that in this sense, this set is not norming for this tensor product. Okay. Second thing is that it is known that if one of the factors X or Y star have the approximation property, or the metric approximation property one, I think it's metric approximation property, it implies that the set of rank operators are actually norming for the space. And we don't want that. So we have to look for our context sample in the context of Banach spaces failing the approximation property. And plus, because of the thing that I just mentioned before, we have to guarantee somehow that the operators which change the norm is not bigger than the finite operators. So we have to put this together and then think on a context sample that it can work all these properties here. The first thing that pops up in your head is the Miguel context samples on compact operators, because he was doing something like this. And actually, this is, I would say that this is not an adaptation, but at least Miguel gave us the first steps to think in this context sample. Okay, and which is the context sample? The context sample, you take the rad space. So there exists a subspace X of C0 and Y in the rad space, such that the set of tensors in X times Y star, which attain the projective norm, is not dense in this space. Okay. So why rad space? Because in the rad space is a renorming of C0, which has bidual strictly convex. And then in this case, we can apply Miguel's result. They're the same one that I showed you before. So that's the idea. Okay. Okay. So I commented like this. So let's like I commented before. I will finish with open questions and some further research on the topic. So the first question that we don't know is the following one. So when Y is finite dimensional, is it true that the set of all nuclear operators Y from Y to Z always attains a norm for every Banach space Z? So we don't know this question, and actually, if you think a little bit of it, this will give actually that finite dimensional have property B of Lindenstrauss, which turns out to be a very difficult question. Okay, so I think I would bet that this is a very difficult question, at least for us. The second one is that we don't know that if both factors are reflexive, then you have denseness or not. So we don't know this. Now we are trying to tackle this problem again, but we don't know the answer for this question yet. And finally, we don't have a context sample of two Banach spaces X and Y, so that the set of NA is not dense in NA in N of XY. So actually, at that time, I remember that we were pretty feisty in this sense, that we were trying so hard to get this context sample here. But at the end, we tried to mimic that proof, that the first context sample that I was talking to you before on the tensor, and it doesn't work for some technical reason on the kernel of the J that I was talking about before. It doesn't work, the proof. So I would say, and I would bet that the context sample for this case should be totally different from the one that we have. Okay. So for the research on this topic, so nowadays we are working with Luis Carlos Garcia Lirola, Mingo, and Abraham on projective symmetric tensor product. So in this space, you can give the natural definition again of what we mean by a norm-attaining tensor in this case, and we actually have the same characterization, trying to get rid of the language of tensor products and put it now for homogeneous polynomials. So we have already several results on this topic in this direction, but I will. This is another story, and then maybe someone else, maybe Luis Carlos could tell this story in a few months, or whatever. And yeah, that's the thing that I would like to share with you. And thank you very much for your attention.
Thank you, Sheldon. Any questions for the speaker?
I have a question. I don't know if maybe I missed something or misunderstood something, but when one of the Banach spaces is finite dimensional, you have that the Norm-Attaining elements in the tensor products are dense. But it is not that one of them or two of them?
No, both. Both of them must be finite.
Ah, okay.
For just one, we don't know the answer yet.
That was my question. I didn't understand that. Okay.
Yes. For both.
You mean that both of them have finite dimensions so that you can ensure that you have denseness?
The denseness, yes.
But in that case, is it, maybe it's obviously false, but is it possible that you have denseness of the elements that attain their norm in a finite sum? Because you have, the tensor product is also finite dimensional in that case. So maybe the projective norm can be attained with a finite sum, not an infinite sum. I don't know if I'm clear.
Yes. Yeah, I don't know. But I would think about it. Maybe. But I remember that we were struggling with this for a while, and then we couldn't make it.
Okay. Good. Thank you. Very nice talk, by the way. Very nice.
Thank you.
Sheldon,
Dime, Manolo.
it's not true that whenever the origin is finite dimensional, any operator is nuclear?
Yes, I guess so. It's with norm smaller than, yes, I guess so, yes.
No, because you asked if the norm is the nuclear operator when the origin X is finite dimensional. Is that the question? Maybe I misunderstood your question. Go back to your question.
Yeah, finite rank operators are nuclear, so they are nuclear always.
Yes,
this is the point. Nothing more, okay?
Okay, Manolo, yes. Now I got it.
Thank you.
Okay, if there are no more questions, we thank again our speaker.
Okay, thank you. Can I stop sharing here?
Yeah.
Okay.